Okay, so what we're going to look at today is something called uniform circular motion. This is an extremely important topic for people that are interested in pretty much any realm of science: physics, chemistry, biology, engineering. It's a big part of engineering. It's also useful in sports analysis because in sports analysis, you're looking at all sorts of things like the rotation of objects, the rotation of carts, the rotation of um, any sort of flying object is related to circular motion. If you want to build satellites, you need to understand circular motion. If you want to look at astronomy and how galaxies move, you need to understand circular motion. Theme parks, as you can see here, are a huge part of circular motion. Most rides rotate at in some capacity, almost all rides. And in these rides, the circular motion is super important to understand and to be able to quantify and calculate the forces, the accelerations, what people can withstand, all sorts of things. We can talk about how you can use circular motion to create quote unquote artificial gravity, which is going to be extremely important in space travel. In biology, you use centrifuges to separate plasma from blood cells. And it just goes on and on. The concept in physics, it's used everywhere as well, obviously, since that's where we're learning about it. But even in chemistry and biology, these concepts are extremely important to understand. So take this unit very, very seriously and do your best to learn all of the key concepts. We're going to see in this unit that we can draw back all the way to the fundamental laws that we've learned about. Newton's three laws. The first law of inertia is going to be extremely important in understanding the sensations that you feel and that objects experience during circular motion. The Newton's second law, the net force equals mass times acceleration, is going to be important for doing calculations, determining the forces that occur during centripetal acceleration, centripetal force, and circular motion in general. And of course, Newton's third law, which is the action reaction. We're going to talk about, why it is when you're going in a loop to loop, for instance, why it is the normal force that's pushing you and keeping you on the track, and what sort of the reaction forces are on these struts and on the foundations and on the earth and all sorts of things. And the other part that we're going to obviously tie into is our just very basic kinematics equations, which were derived by Newton using calculus, of course, but nonetheless, we can use them here as well. Okay, well, let's get started on it, and we'll embed some videos in here as well, just to give you some better understanding of things. So what is uniform circular motion? Well, the key word here is uniform. Okay, I think you all get the idea of what circular is. So it is motion that occurs when an object is moving in a circle with constant speed and a constant radius. If the speed is changing while you're going in a circle, or the radius gets smaller or bigger, that is non-uniform circular motion. It's very complicated to deal with. You have to use calculus to solve the problems. So we don't want to go there yet. You can do that if you continue your studies into the sciences and physics and engineering. Now, so if the object is moving at a constant speed and constant radius, it's undergoing what's called circular motion. So something that's really important. The speed of the object remains constant, okay? Key word here, speed. And so does the radius. And I've got a diagram below that you're going to look at. But the velocity vector changes direction. Okay, now, what does this mean? The velocity vector changes direction. And there's another thing you'll see here that says the velocity vector is always tangent to the circle. Well, remember, a tangent line is a line that touches a curve at only one point. So what we're going to discover here is this velocity vector that we have for circular motion is called the tangential velocity. Okay, the tangential velocity. Now, let's draw and look at a situation, and we'll talk about what acceleration is. Now, what you're going to see on the sheet here is on this diagram, we've got a radius r, okay? And it's a vector because it changes direction. It's a radius vector, and we're going to pretend that this is a horizontal surface. Could be just maybe there's a rope, and then you've attached a ball here, and the ball is rotating in a horizontal plane like this, or it's a car going around a circle, or it's a bike going around a circle, or it's a moon orbiting a planet, or it's this Earth orbiting the sun. Doesn't matter. Any horizontal surface you see at this point, we can draw from the center a radius vector out to the object, and then we say, well, what's this object doing? Well, it's moving. It's got some speed, but that speed is tangent to the surface. So that is the tangential velocity. That's the direction that it's moving. If the rope snapped, this object would move in that direction. It doesn't fly outward, doesn't fly inward. It flies off in that direction at that point. So let's look at a point up here. Let me just grab this point. Well, if we're there, what's the tangential velocity? Well, it's not quite straight down, but it's going to be about there because I wasn't right at the center point. And because we can see that if I draw the dashed line, it's not perfectly centered. You can draw yours where you need to. But the velocity vector should be exactly the same size. Mine is not. That's my bad. But you can see that the right here and right here, that there's a 90 degrees. That's the word, it's making a tangent to that point. So that's important. Let's draw another point maybe here. Well, where would the velocity vector be? And you can draw it. Tangent to it. And again, it's constant radius. The length of the arrows should stay the same, but notice something about the direction of them. They're not going in the same direction. So if you recall from before, from basic kinematics, even though the speed is constant, the velocity vector is changing direction, and therefore acceleration is occurring. Acceleration is happening because acceleration is not the change in speed. It's the change in velocity. Now, in calculus terms, it's this. Okay? Since the velocity vector direction is changing, there is acceleration happening. And this is going to sort of bother you for a little bit because you're like, well, acceleration is a change in speed, speeding up, slowing down. That's wrong. It's speeding up, slowing down, or changing direction, or both. So because the velocity is changing its direction, there is acceleration happening. And now I would ask you to think, where is this acceleration? Where's it pointing? Where's it going? Okay, and we're going to not do a rigorous mathematical calculus solution to this for this course, since it's only a grade 11 introductory course. We're going to watch a demonstration to explain where the acceleration is. So, is it outward? Is it inward? Is it this way? Is it that way? Where is it? Like, I have no idea. Where is this acceleration? Well, let's take a look and find out.
In this physics demonstration, I have a turntable. The turntable can rotate in a circle about its axis, and clamped down to the turntable is a wooden 2x4, and secured to the wooden 2x4 are two glass jars. These glass jars are filled with water, and inside the water is an orange cork. The cork is tied by a string to the lid of the jar. The jar is inverted upside down, and the cork is floating within the water. What I'm going to do is spin this turntable. When I do, the jars and the water and the cork inside the jars are going to begin to move in a circle. What we know about objects moving in circles is they experience an inward force and an inwards acceleration. Now what's going to happen here is the object that has the most inertia inside the jar is going to be the object that resists the acceleration the most. And that happens to be the water. On a per milliliter basis, it has the most mass, and thus it has the most inertia, and it resists that acceleration the most. The cork, on the other hand, resists the acceleration acceleration the least.
That's just inertia.
Therefore, the cork's going to lean in the direction of the acceleration, giving us evidence of that big idea in physics, that objects that move in circles experience an inward or a centripetal acceleration. Here we go. There you see it. The corks are leaning towards the center of the circle. The water is resisting that acceleration the most. The cork.
So, oh, my mouse keeps disappearing for some reason.
Cork resists the least. You have inwards acceleration as evidenced by that inwards lean of the cork. You got to believe in physics.
So that's a pretty weird thing to think about. In that demonstration, and I do in class, as it's rotating, okay, the bobs that were suspended in the water pointed inward. And if you were to take those jars and walk or accelerate forward, you would see that bob would accelerate forward. It would go inward in the direction of the acceleration, which is counterintuitive. You always think of things as, because of the inertia, that they're going to resist that change in that motion, and they're going to appear to move backwards. But because the water is heavier and resists more than the bob that's floating in it, there's a net gradient force that pushes the bob forward, which gives us an indication of which direction the object is accelerating. Now, what this means is that the acceleration, and this is the key thing that we're going to learn on the next page, what we get is something called centripetal acceleration. Now, centripetal acceleration is always inward towards the radius. That is the direction of, and that's a C, that is the direction of the acceleration at this point. This is the tangential velocity at that point. So here, the object's tangential velocity is down, but it is accelerating inward. Tangential velocity is this way, it is accelerating inward. What if I put a dot, or let's say the particle was here? Okay, well, you would draw an inward line showing the radius. You know that it would be accelerating inward. And, right now you're probably getting upset because you're thinking, what do you mean it's accelerating inward? I don't see this thing accelerating inward. Now, in that demonstration you just saw, clearly accelerated inward. Those bobs moved in towards the center, which is the direction of the acceleration. But if you were to go in a circle, you say, oh, I fly outwards, I'm flying outwards, I'm falling off, I'm going off at a tangent. But what you're forgetting is that you're being pulled inward, right? There's a force that's causing you to continue in that circle. Even though you feel like you're flying outward because of inertia, and then you're not flying outward, remember, you're flying off at a tangent. This idea that you're flying off at a tangent is that sort of inertia that you're feeling. If you're turning in a car, for instance, okay? Or if if you're rotating a string on a ball on a string, right? You feel it pulling outward, but you forget is that you're pulling inward on the ball. And so that ball is actually accelerating inward. And then you're like, well, it's not speeding up, it's not slowing. Why is it not just pulling itself right in towards the center if that's the way it's accelerating? You're forgetting your idea of inertia. The object's tendency is to fly outward or off at a tangent, but there's a rope or a string or gravity or something that is pulling it inward at every point, accelerating it towards the center. But because of inertia, it doesn't fall in towards the center. And in fact, if you look at if you take these two vectors and subtract them, which is what a delta V does, if you do it at a really small time interval, like here in calculus, you will see that the change in the direction is actually always pointing inward. So it's accelerating inward, not linearly, but centripetally. And that's why there's a C here and not a regular, just an acceleration. Okay, so on this sheet, you'll see here, centripetal acceleration is towards the center. If you can get this concept, is massive, right? It's a big concept to grasp and to understand. So centripetal acceleration and the instantaneous velocity are perpendicular to each other. We already showed that. Okay, this is the video link to that video. Okay, origin of the word centripetal. Okay, so the word centripetal in Latin means centrum or center, and patera or pater, not sure how to pronounce it, means to seek. In fact, no one knows how to pronounce it because it's Latin. Thus, Newton coined the term centripetal, or the word center seeking. Center seeking, centrum, pedal, and there we go. Now, there's misconceptions. You're going to often hear the word centrifugal force. It's wrong. It's not a thing. It doesn't exist. Centripetal acceleration exists. Centripetal force exists. Centrifugal forces, or outward forces, or to flee, you can see here like the word fugitive. If you're a fugitive, you're fleeing the law, and that's where that word comes from. But here you get fugal, to flee. It says that centrifugal forces or centrifugal forces are center-fleeing forces. They don't really exist. Sometimes they're helpful in calculations. That's that sensation of flying out, flying away from the center if you're in a rotation motion. If you're trying to turn a really sharp corner and you don't make the corner because friction's too low and you go off at a tangent, you're fleeing the center of the circle. And so centrifugal seems to make sense, but it's going to mess you up in terms of understanding the real physics, the real things that are happening in these situations. Okay, let's watch a quick video about that.
Very interested in addressing a dangerous misconception. A lot of people think that there is a centrifugal, that's how that word's pronounced, a force that is forcing things out of circles, and things don't want to move in circles because of this force that exists to make them bust out of the circle. And really what's happening is, well, you can watch another video on that, but this is just a quick demonstration video to prove to you that things don't have a force pushing them out of circle. As the ball rolls around and I release does. I'm going to do that a few more times until you completely believe me. See which way it went? All right, what about this guy here? How about this? Whoa, not that fast. See which way it goes? Study carefully which way the ball
always off at a tangent
goes, and you will learn about why the ball is doing that. And the ball, I think, just wants to.
So it's going off at
What?
a tangent.
It wants to go in a straight what? It wants to go in a straight what? Why does it want to do that? Why does everything want to do what it has been doing? This is Newton's first law. So this is a filthy lie, and things simply want to go in a straight line because they have inertia. So if somebody ever tells you there's a centrifugal force, and that's why your arms want to fling out when you're spinning around, and buckets of water that you fling over your head stay full of water, it's not true. That happens because of inertia. And inertia is not a force, it is a fundamental tendency of all things. Goodbye.
Okay. So hopefully that will give you a little bit more emphasis about the idea that centripetal and centrifugal are two different things, and the idea that inertia is such a huge part of this. Okay. The magnitude of the centripetal acceleration. We're not going to get into all the derivation of this. It is quite it's somewhat complicated, involves calculus, but what we're going to see is that there is a derivation that can be done. You can search it. I can post it on the website if you're really interested in seeing the derivation for centripetal acceleration. And then you will notice that it is a very simple formula. So if you want to calculate the magnitude of the centripetal acceleration, it is v squared divided by r, or the tangential velocity squared divided by the radius r. Now, let's check the units. The top is meters per second squared. So both the meters and the seconds are squared. And on the bottom, it's meters. The meters divides out with one of those meters, and you're left with meters per second squared, which is units of acceleration. So the units work out. A lot of times people forget to square the m or the v, so be careful with that. Now, often the speed of the object isn't known, but the radius and period are. Since the speed is constant and equals the circumference of the circle, and hopefully you understand the circumference of a circle is 2 pi r, and you divide it by the period of revolution, which in grade 11 we learned is capital T for period. So what you can get is this is circumference divided by time. So if I said, hey, how fast are you driving around a circle? How fast did you run in a circle? Or how fast did the Earth orbit the sun in a circle? You say, well, how far did it travel? Well, it traveled 2 pi r distance, which is the circumference. How long did it take? It took 365 days, or it took 25 minutes, or whatever the case may be. It took time. So the tangential speed is 2 pi r over the period t. Now, what we can easily show is that the centripetal acceleration is 4 pi squared r over t squared. And you're like, okay, how do we get that? Well, let's do it really quickly. Again, you can do it on your own. If you want to hit pause, I would suggest doing that. So the centripetal acceleration is v squared over r. But we just said that v is 2 pi r squared over r. And by over r, oh yeah, and then there's t squared as well. Because remember, it's 2 pi r squared, and then the t also has to be squared. And since it's on the bottom, we put it there. And that leaves us with 4 pi squared r squared over rt squared. And then you have the r and the r squared divide out. One of them does, pi squared r over t squared. Okay, so that's how we get to that. Now, we know one other thing. Frequency and period are reciprocal of each other, right? They're reciprocals of one another. Remember that frequency is measured in hertz, which is 1 over seconds. Period is time, so it's measured in seconds. So 1 over seconds is called a hertz. And it's good to refresh yourself on that little bit there. So now we know the centripetal acceleration is v squared over r, which is the same thing as 4 pi squared r over t squared. And then if we just realize that period is 1 over frequency, then if we replace t squared with 1 over frequency squared, it flips to the top, and we get 4 pi squared r f squared. If you're having difficulty with that, that's just some basic math that you're going to need to refresh yourself with, maybe try it out to make sure that you understand how 1 over t squared is the same thing as f squared. So 1 over t squared is the same thing as f squared. So if you know the frequency, the radius, you can figure out the centripetal acceleration. If you know the period and the radius, you can figure out the centripetal acceleration. If you know the speed and the radius, you can figure out the centripetal acceleration. You can just put your finger over top of which ones you don't want to determine the equation that you wish to use. You can even do this to solve for v squared or v. You could do that to figure out v. Any manipulation of these things by covering up 2 of them is extremely useful when you're solving these problems. Big take homes: centripetal, center seeking. It is inertia that gives you the sensation of that outward force, but it's really just a tangential speed. It's the object's, whatever it's confined in, that's causing it to change its direction. Tangential velocity is always tangent to the surface, to the circle, and the centripetal acceleration is perpendicular to that and always pointing inwards. It's very simple to calculate the centripetal acceleration as well. So what you're going to do now is work on the basic problems that have been presented to you. And if you're interested in figuring out how v squared over r came about for centripetal acceleration, you can research that online. and sort of brush up on your calculus. Okay, so that's about it, and good luck on the problems.